Hello, everybody. In this video, we are going to continue the discussion on the viscosity, and we are going to discuss like a very important point, which is the dependence of the viscosity on temperature. Um, and this is one of the very important things that we need to know about viscosity, because the temperature is one of the factors that have very big influence on the viscosity of fluids. And we'll see yeah, more about this in this video, and I think this will relate to a lot of things that we can observe ourselves. So to understand the effect of temperature on the viscosity, we need to know first why or what is the cause of the viscosity, or how the viscosity happens in liquids and in solids, because this will clarify the effect of temperature. The reason of viscosity in liquids is different from that in gases. For liquids, the viscosity is, and this is something we mentioned before in when we saw the video of different or for liquids that were poured in the same time for the same distance. And we said that the viscosity is due to the cohesion force between, or the cohesive force between the liquid particles or the molecules. And as the liquid molecule cohesive force increases, the viscosity increases, because it's going to be more difficult for the particles to slide over each other, or for the molecules to slide over each other. So the effect of temperature is on the viscosity is mainly the effect of temperature on the cohesive force, and it's very well known that the high temperature leads to lower cohesive forces. It weakens the forces between the molecules. So as the temperature increases, the cohesive force decreases, and so the viscosity decreases. So this is why the viscosity decreases with temperature, and this is something we will see in more details later, because this is something we can easily observe in our daily life. On the other hand, for gases, the viscosity of gases is result of a different reason. It's a result of the collision between the molecules. So as the collision between the molecules increases, the gas becomes more viscous, and so the increase in temperature, we know that the increase in temperature leads to an increase in the energy of the particles of the molecules of the gases, and so the particles or the molecules will move more, and then the collision will be more, and so the viscosity increases. So it's a different effect. For liquids, the increase in temperature leads to reduction in the viscosity. For gases, the increases in temperature leads to increasing the viscosity. I know for the gases it might be counterintuitive, but this is how it works. So for this graph shows how the viscosity changes. For liquid, it decreases, and for gases, it increases with temperature on the x-axis. So this is like a good thing to know about the viscosities. Now, one of the things that we are interested in is to know how to predict the viscosity, or to know the viscosity of a specific fluid at specific temperature. This is like a very like wide topic, and there are a lot of work that has been done to produce equations like this. There are equations that are valid for organic compounds, for polar components, for whatever. So there are a lot of equations. There are like hundreds of equations, I would say, or tens of equations that are produced to predict the viscosity. What we are going to see now is just an example, just to know how the equations will look like. For gases, there is a correlation that is called the Sutherland correlation, where you have here the viscosity as a function of temperature, and there are two parameters, A and B. A and B are constants that are experimentally determined for a specific gas. So A and B depend on the type of gas, and the T is the temperature. What you will do is you'll just find the values of A and B for the gas that you're interested in, and then plug the temperature in the equation with A and B and calculate the viscosity. So it's as simple as this. But the point I want to refer to here is that we need to make sure that what we just mentioned about the effect of temperature on the viscosity is valid for this equation. So if the temperature increases, then this term will decrease, and so the whole denominator will decrease, and so it increases the whole term. And the same for T, as the temperature increases, the viscosity increases. So this equation confirms the what we just said, that as the temperature increases, the viscosity will decrease. For liquids, there are other equations. We have this equation that we can use for some liquids, and the same thing. It's A, B, C are constants, and T is the temperature. You just put the constants for the liquid, and you calculate the viscosity. Again, let's check how the temperature affects the viscosity. The increase in temperature leads to decreasing the whole fraction, and then it decreases the power of 10. So this 10 power B over TC will decrease, and then the viscosity will decrease. So it works. So now one thing that I want to refer to, when this is an important thing, is to have some feeling of the effect of temperature. Is it really so significant in the viscosity, or in on the value of the viscosity, or not? So if you look at this table, we have here some fluids at different some different fluids at different temperatures and their viscosities. I want to just spend some time to look at the numbers in this part, because this is really important. If you look here, this is just an increment of 20 degrees Celsius from here to here, and this is 20 more Celsius, and this is 20 more degrees. And you see the temperature here is decreased by more than 10 times. So this is 134 became 10.5. This is for glycerin, of course. And 20 more degrees increase in temperature, it reduces it by 10 times. It's 10.5, it becomes 1.5. And again, it increases a lot. So the temperature is significantly affecting the viscosity. It's not just something that affects it in a simple way. It has a very significant effect on the viscosity. We have here also some other viscosities for different materials. This doesn't relate to the temperature, but there are some notes that I want to make here. The first is that the viscosity of liquids is orders of magnitude higher than that of gases. If you check here, for example, for liquid water, let's look at these two numbers. Okay, so this is liquid water at 100 degrees Celsius, and this is water vapor at 100 degrees Celsius. It's the same material at the same temperature, but the only difference is in the phase. The viscosity here is increased by from the vapor to the liquid. It's more than 20 times. Okay, so it's order of magnitude higher. The same here if you look at the values for liquid water, and of course the effect of temperature is clear here. But the thing here is that, for example, let's see for gasoline or ammonia, air and hydrogen, these are all gases, and look at the liquids. The viscosities of liquids, it's a very different range. These are 10 power minus 1, 10 power minus 2, 10 power minus 3. Here these are 10 power minus 4 and 10 power minus 5 and even 10 power minus 6. So the viscosities is higher for liquids, significantly higher than for gases. And we said this, the viscosities of liquid increases by orders of magnitude. Of course, this is not for all the liquids, but for some liquids, for this order of magnitude thing. And here this is one interesting video that shows how the viscosity affect or changes with temperature. So this is a marble. So just let me give you a hint about this. So this is a cylinder filled with honey. It's a container filled with honey, the honey that we drink. And we are doing the experiment at 3 different temperatures. And the experiment is simply dropping a marble, the glass marble that kids play with. It's a glass marble that is left to fall freely in the cylinder that is filled with mercury. Here, this is honey at 50 degrees Celsius, Fahrenheit. 50 degrees Fahrenheit, I would say it's around, 20 Celsius or something. It's around 20 Celsius. And this is honey at 100 degrees Celsius, Fahrenheit, which is around 37 degrees Celsius. So here you would see that the marble is falling, okay? And this is an interesting thing here. There is a marble here already, and if you look here at this part, this is a marble. It's moving very, very slowly that you cannot even notice that it's a marble. So let's play the video. So at 100 degrees Celsius, 37 degrees, it's very fast compared to the one at 50 degrees Fahrenheit. Now we have another one. So this 100 Fahrenheit is cylinder is removed, and we have another one that is at 70 degrees Fahrenheit, and there is another marble that's falling, and still this is left to fall. And you see it's falling very, very, very slowly, while this is falling quicker than the other one. So this is a good video to show how the temperature affects the viscosity of different or of liquids. There is one last thing that we are going to mention here. It's mentioned in the textbook, and it's a good thing to know that how to measure the viscosity. There are many ways of measuring the viscosity. There are equipment that are used to measure the viscosity by dripping a liquid from a standard container and seeing how much time it takes, and this time represents the viscosity in a way or another. But there is another equipment that we are using here, or we are going to discuss here, which is called the rotating viscometer. Okay, this rotating viscometer, just to understand how or what it consists of. This is it consists of, as you see here, this is a side view. It consists of two concentric cylinders. There is one cylinder here, which is an inner cylinder, and there is one outer cylinder here. The radius of the inner cylinder is R, and the outer cylinder is R plus L. The small l, it's the spacing between the two cylinders, and they have a length L. Okay, so if you look from the top, this is the top view of the viscometer. Okay, the outer cylinder is stationary, so it doesn't move, and the fluid that we want to measure the viscosity of is poured here, or fills the spacing between the two cylinders. And the inner cylinder, it's not hollow, it's closed cylinder, and it can rotate with speed n dot in rotations per minute. Okay, and if you think of this, it's very similar to the parallel plate experiment that we did before. In this case, we have two parallel surfaces, but it's two cylinders instead of two parallel plates. So this is the stationary plate, this is the moving plate, or the stationary surface, and this is the moving surface. And then the velocity here is high. As you see here from the velocity profile, the velocity here is the highest, and it decreases until it reaches the stationary cylinder. Okay, so this is simply how it works. And of course, for this cylinder, the inner cylinder, to rotate, it has to exert some force to overcome the viscosity of the fluid. And this force can be translated into stress or torque. So this machine can measure the torque that is applied by the inner cylinder to rotate and overcome the viscosity of the fluid. And given the dimensions of the cylinder, which we definitely know, and given the speed of rotation that we can adjust the machine to, and given the torque that the machine can measure, we can find the viscosity. And we can do this by doing simple derivation that we are going to do here. So the n, which is revolutions per minute, this is how many revolutions the cylinder is rotating per minute. It's equal to the angular velocity, which is how many radians per minute, and we multiply it by 1 over 2 pi. One revolution is equivalent to 2 pi radians. So it's omega over 2 pi. So this n, it's how many revolutions per minute, can be expressed as omega as 2 pi over 2 pi, or omega can be calculated as 2 pi times n, where n is the rotations per minute. Okay, and the tangential velocity, which is the velocity at this surface, the parallel or perpendicular to the radius, the tangential velocity, which we can see here from this velocity profile, is omega times r, which is 2 pi n times r. So this is the tangential velocity. Now, as I told you, we can consider these two as two parallel surfaces. So we can apply the, or before this, we know the area of the cylinder, which is the area that is exposed to the fluid, and it's resisting or applying shear force to resist the fluid viscosity. It's 2 pi RL, which is the inner surface of this, or the surface of the inner cylinder. Okay, and the force exerted is equal to tau times A. Tau, as I told you, this can be expressed or considered as two parallel surfaces. So we can consider this as, and if we have the Newtonian fluid, we can apply the Newton's law, which is mu times V over L. V, it's delta V, which is V minus 0, which is the velocity here is V, which we calculated here. And this velocity here is 0, so it's V over L, which is the distance between the two surfaces, the two cylinders. So this is tau, which is mu times V over L, times the area, which is 2 pi RL. So this is the total force exerted by the inner cylinder. Multiplied by the area. So we have here, this is the total force, which is the shear stress times the area. And of course, we want to express this in terms of the parameters that we know, which is the rotations per minute, the dimensions of the and the dimensions of the machine. So mu is what we want to calculate or measure at the end. So we will keep it as it is. The velocity is 2 pi n times r. Okay, and this is I think and this is I think there's something wrong here. No, it's 2 pi nr. I think I just missed the n here. It's missing here. I forgot. No. So it's 2 pi rl. This is the area. Oh no, it's right. So it's I'm just rearranging the equation. It's mu times 2 pi rl times v over l. So I put everything together, and here the v is replaced by 2 pi nr. Okay, so this is the velocity, 2 pi nr. Okay, so now by simplifying the equation and combining the same terms, so it's 2 times 2 is 4, pi times pi is pi square, n r square l over the small l. So this equation is the force, and we don't know the force, but we know the torque. And we know the torque is the force times the radius. So it's mu times this whole equation. It's the same, but it's r power 3 instead of r power 2. So this is the torque of the machine will measure. So if we know the torque, and we know the dimensions of the machine, and we know the rotations per minute, the n, we can calculate the viscosity. So this is simply how we can calculate the viscosity using the viscometer, and that's it. So let's just look at this example here. We have a fluid whose viscosity is unknown, and we want to measure, and it's constructed of two 40 centimeter long concentric cylinders. The 40 centimeter is the length of the cylinder. Both cylinders, of course. The outer diameter of the inner cylinder is 12 centimeter. So this is the diameter, it's 0.12 meter, and the radius is half the diameter, it's 6 centimeter. The gap between the two cylinders, which is the small l, is 0.15 centimeter, which is 1.5 times 10 power minus 3 meter. The units here are very important. You need to make sure that all the units are consistent. The inner cylinder rotates at 300 RPM. So this is the speed, 300 RPM. And of course, we are using SI units. So 300 RPM is 5 RPS, which is rotations per second. And we know the torque is 1.8 Newton meter, so we want to calculate the viscosity. It's going to be very straightforward. You're just rearranging the equation, put everything together, and substituting with the numbers with the proper units, and then you can calculate the viscosity to be 0.158 Pascal second. So it's a very straightforward thing, and it's an easy way of measuring the viscosity of fluids, of liquids, of course. So by this we end chapter 2, or what we cover in chapter 2. Next time, inshallah, we are going to start chapter 3, which is about fluid statics. So I'll see you then, inshallah.